Okay, let's jump into chapter 2. We're going to talk about water. May be interesting that we have a entire chapter devoted to water, but water is a very interesting and unique molecule that is very important for life, or you could say that life evolved to take advantage of the very unique properties of water. Again, here's the key concepts. We'll hit on these. They're also found in your study guide. And this is just to direct your study so that you know the key points that you should be getting out of the lectures and your reading. So we're going to talk about kind of two different sections. One, just the physical properties of water. And that will stress that water is a polar molecule. We'll talk a little bit about how hydrophilic substances dissolve in water. Talk a little bit about the hydrophobic effect and the interaction of water with nonpolar substances, and just briefly talk about osmosis and diffusion. And then the second section is actually the chemical properties of water. And this will really just be acid-base chemistry discussion. So the main part is actually just physical properties. So we're just going to look at the structure of water and start to understand its physical characteristics. And then the chemical would be when we start talking about making and breaking bonds. Now I've got this little interesting graph down here that if you just took essentially the hydrides of the elements, including oxygen, so sulfur, selenium, tellurium, then you can see their boiling point. And you can see that it actually trends downward. So H2TE has a boiling point of -2.2. Hydrogen selenide has a boiling point of -41.3 degrees Celsius. So that tends to be a gas at almost all physiologically relevant temperatures. Maybe in Siberia, it might get below -40 Celsius. And then you can see hydrogen sulfide there, -60. So if you look at this prediction there, then water should actually be at -80. That's when it should actually turn into a gas. So there's something very unique about water. It doesn't fit this trend there. And in fact, it's very far off. In fact, it has a boiling point of 100, quite a bit higher than similar molecules. So just going from oxygen to sulfur has a huge difference, and that is water. So one of the key things that makes water different is its ability to hydrogen bond. So down here, I actually have across the row, you can look at the boiling points, and you can see that you go from methane that has a boiling point of -161 degrees Celsius to ammonia that -33.3 degrees Celsius to water. All of a sudden, it's got a really high boiling point. And then you got hydrofluoric acid that kind of drops off. So even across the row, you kind of see an anomalous trend. Hydrofluoric acid, you might guess, actually would be a little bit higher, where in fact it's actually lower than water. And then you can look at the row right beneath it. So the third row elements, silicon, phosphorus, sulfur, and chlorine. And you can see that those actually have much more similar boiling points. So again, there is something very unique about those elements. In fact, if you look in red, nitrogen, oxygen, and fluorine, they all kind of have this uncharacteristically high boiling point. So there's something unique about those molecules. And what it comes down to is hydrogen bonding. So up in the top right, you will see some schematics of molecules hydrogen bonding. And we'll talk about that more in detail. You should know a lot about hydrogen bonding, but essentially what it is it's an interaction between a lone pair and a electron deficient hydrogen. Now, if you're in my OChem class, I stress this quite a bit, that what it is hydrogen only has one shell of electrons. It's got those electrons in the s orbital. And so if it's attached to a very electronegative element, essentially you're stripping that one shell of electrons from around hydrogen and somewhat revealing its proton. So I say its proton is showing. So essentially its nucleus is becoming exposed. And you can imagine the attraction between electrons and a proton or an exposed nucleus is going to be a very strong interaction. The negative charge of electrons with the positive charge of protons should be a very strong interaction. And that only occurs when hydrogen is attached to very electronegative elements, what I refer to as the fun elements, fluorine, oxygen, and nitrogen. And hydrogen bonding is so fun to talk about. And so when these elements are bound to hydrogen, they essentially pull those electrons away by induction, revealing or somewhat exposing the nucleus there. And then you've got these lone pairs on other elements. Again, the fun elements, fluorine, oxygen, nitrogen, that actually can form a fairly strong interaction between there. So hydrogen bonding is very important. It's what holds proteins together, or at least one of the intermolecular forces. Proteins that we will talk about in depth are important for structural purposes, but they also fold into these shapes that allow them to do reactions. And so there are biological catalysts. So many of the reactions that we rely on for life, if we did in a beaker, wouldn't run very efficiently. And so we need a catalyst for them. In organic chemistry, we tend to use metal catalysts, but in biology, we tend to use these protein catalysts that often also use metals. And again, we'll talk quite a bit about that in detail, but just for this point, understand that hydrogen bonding is very important biologically. It's also what allows fidelity of genetic information by base pairing. So the base pairing between the nucleotides, which is our next chapter, is what allows us to have information and a copy of that information. And then we take that information and use it to create proteins that then do reactions and essentially allow life. So hydrogen bonding specific in DNA is very important. Again, that's why we're talking about hydrogen bonding. So let's just look at the physical properties of water. So often we just represent water as these ball and stick models. And something that we do poorly in organic chemistry is we tend not to talk about really the full area that the electrons take up. And in essence, you know, we look at water and we look at this ball and stick, but it's more like Mickey Mouse ears. I don't know if you've seen that before, but the shape of water really is kind of just bumps and nubs instead of these ball and sticks. And so we got these bumps where we get this partial negative on the surface, and then we got these bumps that are kind of partial positives. But really molecules are somewhat globular. They don't have a lot of really defined shape, and that is what's referred to as the van der Waals radius. That's the radius that, if you actually looked at where the electrons are occupying, that is the space taken up by the electrons around the molecule. So again, these line drawings and ball and stick drawings really kind of underestimate the size and just kind of the general lack of shape that molecules have. And so we'll find out that really it's not the shape, it's going to be the electron rich and electron pore sites in kind of this globular structure of molecules. Again, we're used to seeing this, and that kind of makes sense to us, but as we get into it further, we'll realize that things really are just kind of a smear, and then in that smear, we'll have these partial positives and partial negatives that give rise to their properties, especially with much larger molecules. So water has 2 bonds to hydrogen, needs an octet, so it also has 2 non-bonding lone pairs. The bond angle between the atoms, the HOH bond, is around 104.5 degrees. We've always been taught that that's due to the lone pairs requiring more energy. So by VSEPR, that actually kind of forces these electrons closer together. I just found out this summer that that's kind of a lie, and this shape is actually due more likely to the type of orbitals that are interacting with the oxygens here. Due to the overlap of the s orbital with the oxygen there, that tends to constrain this bond angle there. Either way, we can run with it that the bond angle deviates from a pure tetrahedron, and so the bond angle here is less than what we would expect for a pure tetrahedron of 109.5, so closer to 105-ish. And again, those lone pairs are available to be involved in reactions and also are able to form these hydrogen bonds that we can see over here to the left. So again, the requirement for a hydrogen bond is really the fun elements. And again, that's somewhat of a lie too, because really what a hydrogen bond is just a dipole-dipole interaction, a permanent dipole. And that permanent dipole comes when you have an electronegative element attached to a less electronegative element. And we can actually see that permanent dipole right here in this ketone group. And so this dipole right here, molecules don't like to be left alone with the dipole. And so what happens is we get attraction between these opposite charges. And so we would get attraction between the dipole on that oxygen with that carbonyl. But when we get a interaction between a lone pair and a hydrogen that's attached to the electronegative element, we refer to that as a hydrogen bonding. It just happens to be an especially strong dipole-dipole interaction. And so when we talk about how strong it is, well, it's actually pretty weak. So covalent bond, so to break a OH covalent bond, that's 460 kilojoules per mole. To actually break a hydrogen bond is only 20 kilojoules per mole. So in relationship to covalent and ionic bonds, hydrogen bonds are actually fairly weak, but they are one of the stronger intermolecular bonds. So in water, these individual water molecules will form hydrogen bonds. So we've got the hydrogen bond donor, which actually has the H that it's donating, and the hydrogen bond acceptor that has the lone pair that's accepting that hydrogen bond. And so in water, what happens is you get some hydrogen bond donation between the individual oxygen atoms and other hydrogens. Now, these interactions actually are rearranging really quick, roughly every 2 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ 0.000000002 seconds. And you can go back and rewind and see if I actually got the right number of zeros in there. I don't think I did, but essentially these are reorienting very, 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 very fast. And what that means are these hydrogen bonds are breaking and forming at really just an unfathomable rate. And so what happens is, and they've done studies and they show that you kind of get these either 3-membered rings or kind of 4-membered rings, or maybe even 5-membered or 6 or 7-membered rings. But they will quickly orient to form new 7-membered rings or new 5-membered rings. So they're just rapidly fluctuating. How I talk about it is this hydrogen here is really just being shared by a lot of other different oxygens in there. Okay, so we get these clusters. Now, what's different is if we cool the temperature down, we actually will get ice, and these molecules will actually adopt a tetrahedral structure. Now, if you look at this ice here, and you ladies, or maybe you guys out there, you look on your ring and you got something sparkly made out of carbon, this structure right here is the exact same form that you get of carbon, these tetrahedral arrangements. of where every atom essentially has 4 bonds. So in ice, the structure is very similar to what you find in diamond. The difference would be that this would be a carbon, and all these carbons would be connected to 4 other carbons. Now, the bonds, again, here in ice are actually just hydrogen bonds. So they're a lot weaker than a carbon-carbon bond. In fact, you heat it up just above 0, and all of a sudden these bonds are going to start to break and the water molecules reorient. Now, something interesting, when we actually form ice, it's one of the few solids, and there are others, but it's one of the few solids that actually becomes less dense. And what that means is as these water molecules go to this tetrahedral shape, they actually take up less volume than when they are in a liquid form. So in a liquid form, they're actually packed together a little bit closer. In fact, water is its most dense at about 4 degrees Celsius. And then as you start to heat it up a little bit on its way to boiling, it decreases its density until it turns into a gas, and then its density is very, very small. But as it turns into ice, its density is 0.92 grams per milliliter. And I've always had fun talking about this. I like to ask students, just think about what would happen if the density of ice was even just 1.02 grams per milliliter. So like most solids, it's more dense than its liquid phase. In fact, it's really interesting. You can actually take the isotope of water, D2O. So deuterium just has an extra neutron, just like water in almost all aspects other than it has a mass of 20 instead of water having a mass of 18. It's not the mass, but density. So when D2O, deuterated water, is actually in its solid form and you put it into regular water, so I have a solution of H2O and I had solid D2O, it will actually sink. So you can actually take an ice cube of water, deuterated water or heavy water, put it in regular water, and that ice cube will actually sink to the bottom, just because heavy water, when it is in its ice form, actually sinks. But if you actually took the ice D2O and put it in liquid D2O, it would actually float. But anyway, just think about that. Just think what would happen if in the world, if ice, when it forms, it actually sunk to the bottom. Now let's think about a lake up in Michigan, or even up on top of Cedar Mountain, Navajo Lake. I think someone said a week ago it still had ice on top of it. And that's what we say when the lake freezes. Oh, it's got ice on top of the lake. And you drill through and you catch the fish underneath. Well, what happened if the ice actually sunk to the bottom? Well, as it got colder and colder and colder through the winter, then all of a sudden the lake would freeze solid, and those fish would be found on top of the lake. And I might be able to actually catch a fish when it was finally frozen solid. You'd go to the lake and you could just pick them up off the top if ice was more dense. Now, the problem is when it gets warm in the summer, you'd only start to melt the top surface of the ice. Usually at really deep lakes, it's really cold down at the bottom, near 4 degrees Celsius. So if you've got a layer of ice at the bottom, you're probably not going to melt a very deep lake. And then when winter comes, it's going to freeze again. So you're going to have a hard time establishing life in that type of system where, let's say, I don't know, yeah, Michigan, Canada, there you go, Alaska, where maybe you've only got 3 or 4 months where even the top foot of the lake would actually be frozen. You're not going to have a very good chance of establishing life. So that's a what if scenario. But life does exist and ice does float. Thank goodness, because if it didn't, I think would have a hard time establishing life. So when we look at the interactions between molecules, we just talked about hydrogen bonding. And so we talked about it being a fairly weak interaction compared to covalent interactions. Now there's actually stronger interactions, and those are ionic interactions. So usually we say, oh yeah, that's due to hydrogen bonding, but yeah, the interactions between ions actually are quite strong. And that's why it takes a lot of energy to melt salts and not as much energy to melt hydrogen bonded liquids like water. And then you've got dipole-dipole interactions that we just talked about, and those are about half as strong as hydrogen bonds. And so if you start looking at a spectrum right here, you start realizing, gosh, hydrogen bonds really aren't as special as I've been taught my entire chemistry life. And so I always hate to break it to students, but hydrogen bonds are simply a special case of dipole-dipole interactions. And in fact, London dispersion forces that aren't very strong, weak, they're just dipole-dipole interactions. They're only momentary dipole-dipole interactions, but nonetheless, all these interactions right here are electrostatic. They are interactions between a positive charged molecule or part of a molecule and a negative. For ionic, those are permanent charges. In hydrogen bonds, those are permanent dipoles, again, with the Fon elements and essentially hydrogen that can have a naked nucleus or have its protons showing. Then you get the dipole-dipole interactions that aren't quite as strong. And again, when we start pulling electrons away from carbon here, carbon's got layers of electrons, kind of like an onion, and you're not going to pull away enough electrons to expose its nucleus, so therefore the interactions are going to be weaker. And then you got London dispersion forces that again are just momentary, and so those are very weak. But if you have a large enough molecule, they can add up to be a significant amount. And so those are the type that we typically talk about, but there's other types of intermolecular interactions, and we'll see them throughout this chapter. So we got kind of that charge to charge, that's the ionic. Charge dipole, we really didn't talk about that, but it would make sense if a molecule's charged that a negative oxygen would interact with it. It'd probably interact more with those hydrogens in hydrogen bonding, but there is some interaction between this positive and that negative there. You've got dipole-dipole interaction. For some reason we lost our oxygens there, so we'll put those back. So you would get the negative here interacting with the hydrogen there. Again, those are what we refer to as hydrogen bonds, but you can actually have dipole-dipole between anything that has permanent dipoles. And then you can have charge and induced dipoles. So if this guy was charged here and it came into proximity of a benzene ring there, that positive would start to pull some of the electrons toward it. And then that would leave a deficiency on this side. So what's happening is this charge on the ammonium is actually inducing a charge on this, what we would refer to as kind of a non-polar, but it can pull those pi electrons towards itself. And you can have the opposite where you could start to get the electrons negative here that are starting to be attracted to the hydrogen there. Again, these are going to be weak interactions. And then you could have just kind of dispersion, London dispersion forces, where again, molecules just have these momentary unsymmetrical arrangements of electrons. And again, in short amount of time, they would actually rearrange. So these are fairly weak unless the molecules have a lot of surface area. And then of course you got the hydrogen bonds, which again are just these dipole-dipole interactions. Okay. We beat that to death, but I think it's fairly important. So you can look and just see some of these type of interactions here. And we'll move on and talk about how you actually dissolve a solid. Well, to dissolve a solid, what you've got to do is you've got to break those hydrogen bond interactions between water and break the interactions between the solutes. Now, if you have an ionic solvent, an ionic compound, you've got to break those ionic interactions. And sometimes we think that, well, the attraction for the water and the chlorine actually have to be much, much stronger than the attraction for the chlorine to the sodium. But in reality, what we want are these attractions to be roughly equal. If the attraction for the water was so strong, then the water would just stay together. And if the attraction between these ions were so strong, they would just stay together. So what has to happen is they have to have roughly the same energy. And so what happens is the energy to break the hydrogen bond here is going to be roughly the energy that you get back when the water molecule interacts with the chlorine there. Now, you do get an additional benefit. Remember, if we're looking at spontaneous reactions, it's not all about enthalpy, the making and breaking of bonds. It's also about the entropy. And so if we take a solid, we actually get an advantage when we dissolve it. We increase the entropy of the solid because it's becoming more disordered. Instead of being in a very organized lattice, it's now going to be dissolved in water. Now, something that we'll talk about in just a second that's very important is, we actually pay a penalty. We may decrease the entropy of the solvent molecules. Now they're going to be locked around this solute molecule. So they actually become organized. They have to hang around that solute molecule. And instead of being able to flip around with their neighbors and form hydrogen bonds with whoever, they're now stuck with that chlorine, and that pays a penalty, an entropic penalty, for the solvent molecules. But again, we do get a benefit because the solute becomes much, much more disorganized. So when we solvate these ions, water having this dipole can associate with both the cations, and that's going to be the oxygen portion will associate with cations, and then the negative portions of the hydrogens, those partial positives on the hydrogens, can solvate or surround the anions. So you want to think about this. Is the delta G going to be positive or negative when we dissolve ionic solvents? And so it's going to come down to this delicate balance of delta H and delta S, as well as the temperature. And so we do get some energy when we have our ions interact with with the water molecules. And you also get some entropy, but like I said, we do pay somewhat of a penalty because we're going to organize those water molecules around the solute. So the ions tend to gain entropy, but they lose their very strong ionic interaction. So here is the general process. For something to dissolve, you have to break the solvent-solvent interactions, you have to break the solute-solute interactions, and you have to get some type of solvent-solute interactions. And again, if these are too strong, then it's not going to dissolve. So sand doesn't dissolve in water. Those solute-to-solute interactions, essentially sand is covalent. So you're not going to be able to break that covalent interaction in a sand network to get the sand to actually dissolve. Okay, so we can get hydrogen bonding, and you might have noticed before that in this case here, I've got a hydrogen bond donor, and here's a hydrogen bond acceptor, but he actually doesn't have an H bound to a electronegative element. So water is going to be the solvent of choice for our biological systems, and they can form hydrogen bonds and serve as both acceptors and donors with things like alcohols. So it can accept a hydrogen bond, donate a hydrogen bond, it can accept a hydrogen bond, okay, but sometimes it only acts as a hydrogen bond donor if the thing that we're dissolving only has lone pairs. And so we just need to understand that, yeah, water can dissolve a lot of things that don't necessarily have to be able to contribute back a hydrogen bond. They can just be a hydrogen bond acceptor. And so again, those things are going to be oxygens with lone pairs, nitrogens that are bound to hydrogens, or alcohols. Okay, so what happens if we have a molecule that doesn't have those groups, that tends to be very nonpolar? Like I said, water, in order to dissolve something, actually has to break its interaction and then have some attraction for the solute. Well, in some cases, and here we've got this molecule that just has a big long carbon chain, that's going to have only these momentary dipoles. So the interaction between the water and this big long greasy chain is going to be very, very minimal. And in fact, the water molecule we will even say that it's not going to dissolve it. Now we can play a trick and add to the molecule a polar head group. And then this polar head group, now, of course, water would be very attracted to that and be able to solvate it. But this portion right here, this hydrophobic portion, we won't say is really dissolved because there's no interaction between it and the water molecules. In fact, there's kind of a penalty that the water pays. Again, like we said, when water solvates something, it actually becomes ordered and is less able to flip between its neighbors. Now, if all of a sudden we put this big greasy thing in between these water molecules are going to try to arrange in their most stable state, but there's no interaction with that greasy portion. So they almost become kind of locked there. And so it cages the greasy part, and these guys lose a lot of entropy. So water tends to minimize its contact with hydrophobic molecules because there's no stabilizing interaction between those two. So it minimizes its interaction with the greasy part by maximizing its bonds to its neighbor. And so it becomes almost ice-like because then it maximizes its hydrogen bonds, where each oxygen or each water molecule is kind of involved in 4 different bonds, where in just liquid water, there may only be 3 or 3.5 bonds to each water molecule. Okay, so that is important to understand. So water tends to minimize its contact with hydrophobic molecules. So we kind of have this model that if we put something greasy in there, the water actually forms a cage around it, kind of like an ice-like cage, and that decreases the entropy of water. And so the water actually becomes organized. And again, that's because the interactions between water and these nonpolar molecules are very weak. So there's no enthalpic gain to offset the entropy loss, meaning there's no interaction between the water and the solute that actually is beneficial. So this leads to the mantra that oil and water don't mix. There's no advantage to trying to get oil and water. In fact, if you have Italian dressing and you shake it up, you'll get these little globs of oil in your salad dressing. And after a while, you'll see that those globs actually coalesce to a single big glob. And what that does is that maximizes the volume here and minimizes the amount of water that actually has to be organized around that. Here, if you looked, you'd actually have a lot more water organized. So if we maximize our volume here, we're going to minimize our surface area contact around those globules. So hydrophobic things tend to associate with each other in water. Now, like I said, we can get hydrophobic things to dissolve in water if we play a trick and make them charged. And so we can make them charged by putting a charge group on them, and then they become what we refer to as amphiphilic or amphiphatic, or an amphiphile, meaning it has both a hydrophilic and a hydrophobic part, a water-loving and a water-fearing part. So amphiphilic, amphiphatic, those are synonyms. And so an example is just a fatty acid, where we have a big, long carbon chain. Okay, this isn't going to want to associate with water, only has van der Waals interaction, but we do get this head group that could associate and actually have a beneficial interaction with water. And we'll also see that proteins are also amphiphilic. They actually have charged groups and nonpolar groups. And that will be important for the structures of proteins. And what we'll find out are the nonpolar groups tend to associate with other nonpolar groups, and the polar groups tend to associate with water. So these amphiphils may form micelles or bilayers depending on their structure. And again, what these micelles and bilayers do is they maximize the volume, and they cause the hydrophobic part. I shouldn't say maximize the volume, sorry. For, these are different than just pure hydrophobics. What they do is they have the hydrophobic parts congregate together. So all the hydrophobic parts interact with each other, and then you get a sphere of these charged groups that water can favorably interact with. Now, micelles are just these kind of spherical shapes, but you can also get bilayers where you just have a linear run of these polar head groups and then a non-polar interior. So you can imagine that these would make sheets, and that these sheets could actually fold around and actually make a tube. And that tube could be closed off at each end and make a compartment, which we will call a cell. Now, this wouldn't be a very good cell here because the interior of it is all hydrophobic. But if you imagine a bilayer, this will be a very weak bilayer, and it looks more like a tube. But if that bilayer rolled up into a tube and then we closed off the ends, then what we would get is an interior that could be aqueous and an exterior that would be aqueous, which you're not going to get in a micelle. This is going to be non-polar in here. So that's not going to be a very good environment to run aqueous reactions. But bilayers will provide that compartment, like we talked about last chapter, that we need to actually contain aqueous reactant, so we can actually do reactions and increase concentration and get stuff done. So there really isn't a hydrophobic force. We often talk about the hydrophobic effect, but really what it is the nonpolar molecule is minimizing energy by associating the hydrophobic parts with each other. Because if you tried to disperse that throughout the water, you would cause the water to be really organized around every molecule. And that's a pretty high penalty to organize all that water. And so by getting the hydrophobic parts, they tend to just get together. They do have some favorable interaction, not a lot, but some favorable interaction. And that minimizes how much you have to organize the water. So micelles, we have those pretty spherical, but here's actually a computer model here. And so in reality, they're much more dynamic, where they fluctuate and they do expose their hydrophobic interior, and then they'll fold up. And anyway, so in micelles, you do start to expose the hydrophobic interior. And that's actually why soaps work. You do expose that hydrophobic interior of your soap, and then it will attach with grease. The grease goes into the inside. If the micelle was just a permanent block, then it really wouldn't dissolve grease. You need it to be able to dynamically open up, let non-polar things in, and then kind of surround it and carry it away. Okay, we will talk about colligative properties of solutions. So you may remember those from Gen Chem. These are properties that depend on the concentration of a dissolved solute, but not its chemical identity. So these are properties that we refer to as colligative. So if I happen to dissolve 1 molar sodium chloride and 2 moles of sugar, we would see the freezing point depression and the boiling point elevation be the same. So it doesn't matter the type of molecules or ions in there, it just matters how many in there. But we're not going to talk too much about freezing point depression and boiling point elevation here. We're going to focus more on osmosis, because this is an important biological process. So osmosis is the passage of a solvent through a semi-permeable membrane separating 2 solutions of different concentration. And so you can see here that we got lots of water, and over here we actually have some solute, which is blue. And in this case here, what's the membrane is permeable is to the solute, or the blue particles. And so what you could look at is, well, this is a very organized system over here because it's just water molecules. And you could look over here and say, well, that's kind of disorganized because I have water and solute. But if I take this whole thing and look at it, I'm like, oh, wow, that is fairly organized in the sense that the solutes all found in one place. So you could say that, hey, this is my closet in my house, and it's got my shoes and my clothes. And then I'm not very good with my shoes. My shoes are found all throughout the house. I have some in the closet, I got some by the front door, I got some in the garage, I got some in the backyard. And what happens is, yeah, well, my closet, you could say, is organized because it actually contains my clothes. Now, if you look at my shoes, yeah, they're evenly dispersed. And so what's going to happen here are my clothes are going to pass through this semi-permeable membrane, which is my bedroom door, and now you find the clothes all throughout the house. The house becomes much more disorganized, and that is favorable. So entropy is what's driving this. We're moving from essentially a high concentration of water here and a high concentration of solute, and you notice water here is actually decreased in its concentration. It's decreased because it now has other things with it, and the concentration here has decreased because the solute has decreased. So we've decreased the concentration of water by itself, and we've decreased the concentration of the solute here. Okay, so that's osmosis, passage of a solvent or a solute. Anyway, it just has to be semi-permeable, and so you can get membranes that are permeable to different things. We'll typically look at the membrane being permeable to water. Now, what happens in this example here, we've got some solute. This is really concentrated in there. And again, you could say that this is really kind of organized because I have a lot of my solute in a very confined space. And so what's going to happen is the water will move in here. So water tends to move from areas of high concentration to lower concentration. So the water is actually lower concentration here. You could say that it's being diluted out by the solute, okay? And as the water moves through this membrane, notice that the solute doesn't come out here, but as water moves through, the volume actually increases. Now, if we happen to plug that, this water will still move in here, and actually what it does is it starts to create a pressure. And that pressure can actually be pretty significant. So I believe there's some numbers in your book. Oh, I forgot to look those up. But anyway, you can get pretty significant osmotic pressures. Typical atmospheric pressures, 1 atmosphere. Osmotic pressures can be 5, 10, 15, 20, depending on, again, how concentrated this is. And that water moving in here to dilute that out, to increase the entropy there is actually quite a big driving force. And so, yeah, in fact, here's an example. So here are some red blood cells. And so if the concentration of the solutes in the water and in the red blood cells were the same, we refer to that as kind of an isotonic solution. And the red blood cells would just appear normal. If you happen to put the red blood cells into just pure water, what would happen is that pure water would again go into the cell that has a bunch of ions and other things, and it would try to dilute out what is in the cell, and the cells would actually start to swell and they end up bursting, called hemolysis. And if you happen to put it in a hypertonic solution, meaning it's much more salty out here, what you do is you actually pull the water out of the red blood cells, and the red blood cells start to shrink, which is crenation. And so they'll shrivel up. So it would be very important for our body to be able to control the amount of ions. But we can take advantage of this and use dialysis. So dialysis takes advantage of osmosis and the random movement of water, which is referred to as diffusion. So diffusion is random, but we can actually take advantage of that and take advantage of the net movement of water from a high concentration to a low concentration. So if we had this sample right here and it had these red contaminants, and we wanted those red contaminants to decrease, what we could do is put it in pure water. And if the membrane was permeable to those red contaminants are going to move from the high concentration out into the beaker. And you notice now within this tube, I have less of them. I could take this tube out, put it into pure water, and again, those red contaminants would eventually move out. And so we can actually purify large biomolecules by dialysis. And our body actually does something similar in kidneys to purify our blood. And again, the water tends to move from where it's high concentration or it's pure to those solutions. And again, if that membrane is just permeable to water, you'll actually see the volume increase on this side. And so, yeah, there's going to be an increased pressure because you've got more volume here pulling down. So anyway, we will talk more about that. So that is the physical properties of water. I was going to cut this into two, but while I'm talking, let's just keep going. This will be a little bit longer. But then again, our lectures are scheduled for 2 hours. So here's what you should have got out of that checkpoint 2.1. See if I talked about everything, or the book talks about it. And now we're going to go on to the chemical properties of water, and these are the things that we are going to focus on. And that should be an exponent there. I'll fix that. So it should be 10 to the negative 14th. Okay, so we're going to talk about the chemical properties, which means we're going to talk about the making and breaking of bonds. And so water can actually undergo what we refer to as autoionization. It can actually just break apart. So if you just have pure water in there, it will actually dissociate. Now, something about water is if we have 1 liter of water, its concentration is 55 molar. That is one heck of a concentration. And you may wonder how you figure that out. Well, if we know the density of water is 1 gram per liter, and we want to figure out how many moles are in a liter, well, we know that we have 18, or sorry, I said 18 gram. It's, let me back up again, sorry. It's 1 gram per milliliter is the density of water. So water has a density of 1 gram per milliliter. And we know the molecular weight of water is 18 grams per mole. So I'll write down those important facts. 1 gram per milliliter is the density of water. We know that the molecular weight of water is 18 grams per mole. And what we want to figure out is the molarity of water, which is moles per liter. Well, if we just take 1 liter of water, well, we know that we have 1,000 grams of water. Well, if we have 1,000 grams of water, well, how many moles do we have? Well, I've got 1 mole for every 18 grams. Lo and behold, we get roughly 55.5 moles of water in 1 liter. And so if we get 55 moles of water per 1 liter, that is 55 molar. I just realized you couldn't see what I was writing, so let me just kind of walk through that again really quick. So you got 1 gram per milliliter. We know that's the density of water. 18 grams per mole. We know that's the molecular weight of water. And what we want to find out is what's the molarity of water, the moles per liter. So if we have 1 liter of water, that means that we've got 1,000 grams. So what I'm going to do is take the 1,000 grams times 1 mole per 18 grams, and lo and behold, you get 55 moles of water. Well, what's our volume? Well, our volume was 1 liter. So the volume, or the concentration of water in water is 55 molar. And that is pretty concentrated. Most of the time when we look at biological systems, we're going to be talking about millimolar. Now that's important because what we're going to do is make the assumption that the concentration of water isn't really going to change. So we're going to ignore it. So if you look down here, we could actually calculate the Ka of water. How much does the water dissociate? And so what you do is you take the products over the reactants. But again, this concentration here is going to be so large, it's really, the change in it is going to be so small that we're just going to actually absorb it into this equilibrium constant, and we get a new equilibrium constant that's referred to as Kw, or the ion product constant for water. And so you should know that the Kw equals the concentration of the OH minus times the concentration of the H plus. And again, H plus and H3O plus are used interchangeably. Really, H plus doesn't exist because that's just a proton, but chemists being lazy like to use H plus, but it would exist more likely as H3O plus. But if you read in your book, you'd also notice that actually that H plus could exist in other forms like H5O plus, or sorry, what was it? Yeah. Anyway, that H plus can actually exist in kind of a bunch of different forms. Really what it is that H plus is surrounded by a bunch of different water molecules that are making and breaking hydrogen bonds with it. We'll see that in just a second. And just a second is now. So we can get what is referred to as proton jumping. So if up here we actually have a H3O, a hydronium ion, that H isn't really permanently attached here. This oxygen here could start to form a hydrogen bond with that hydrogen there. And as that hydrogen bond starts to get a little bit stronger and a little bit stronger and a little bit stronger, then this oxygen will eventually win that, and that bond will become covalent. And then this oxygen here will just have a hydrogen bond. So you can kind of look at that hydrogen as bouncing back and forth between two oxygens. But if this guy gets the bond here, well, this hydrogen here was involved in a hydrogen bond. Now that this oxygen forms a bond there, then this hydrogen says, well, fine, I'll go and form a bond here. This hydrogen says, well, gosh, I'm not wanted. I'm going to form a covalent bond there. This one says, well, man, I'm going to form a hydrogen bond there. I'm going to form a covalent bond there. And what ends up happening is if you looked at this whole scheme down here, if everyone shifted their ownership of that hydrogen that's in pink there, that H3O plus that we started up here actually ends up all the way down here. So that hydronium ion can actually jump essentially completely through a solution in a very small amount of time. So acid-base reactions are some of the fastest reactions that you'll actually see. And it's because this hydrogen, or sorry, this proton, the H, can actually jump essentially almost instantaneously. So really what it is you got this network of hydrogen bond, and it kind of shifts ownership. And so who actually owns the H? Well, in fact, everyone owns the H. This is just a snapshot in time. In reality, this H right here is being shared, and no one has really fully hydrogen bonds or fully covalent bonds. They're just breaking rapidly. Let's leave it at that. Okay. So a little bit more about acid bases. When you get this autoionization of water, if it's just pure, the actual concentration of the acid and the base that you get is fairly insignificant. The concentration is 1 × 10⁻⁷. Very, very, very small concentration of acid and very, very small concentration of the hydroxide. So if you just have pure water there, this reaction is taking place, but the concentrations are very, very small. Now, if we upset that and we actually add more acid in, the solution becomes acidic. Now, these exponents here, it's kind of tricky because the exponents are negative. So actually, as we get to a smaller number, these numbers are becoming actually larger. So essentially, this is 0.01, and this is going to be 0.00000001. So this one right here has a lot more zeros. That's a lot smaller number than this one right here. So if I increase the H plus concentration, I actually see that negative exponent get smaller. And what you notice is a corresponding decrease in the OH minus. So I've increased the H3O plus, and I'm going to decrease the OH minus. Now, if you compare those two numbers here, and you multiplied them. Now, when you multiply things with exponents, you add the exponents together. So if I multiply these exponents together, I would get 1 times 10 to the negative 14th. Now, in this case here, when I multiply those two together, I get 1 times 10 to the negative 14th. And likewise, if I increase the concentration of the base, again, increasing it there, I would decrease the H3O plus concentration, times those two together, it's 1 times 10 to the negative 14th. Okay. Now, those are horrible numbers to look at. In fact, you're probably just shaking your head and saying, wait, I'm going to a smaller negative exponent, but that's making a bigger number. Hopefully everyone's just like, gosh, that just hurts my head. So it hurts a lot of chemists' heads. So we play this trick, and what we do is we take the negative log of that. And so I'm not going to give you the whole lowdown on logs. You should know essentially what logs do. But a log of 10 to the 7th essentially just pulls down that exponent. And so if I had a log of 10 to the 7th, it would be 7. Now, if I took the log of 10 to the negative 7th, that would be a negative 7 there. So what we do is we take the negative log of 10 to the 7th, sorry, 10 to the negative 7th, and that's actually going to give us a positive number. So if you've ever wondered why it's the negative log, that is simply so we can get positive numbers. And that makes it so much easier to talk about, because now we can talk about a scale from 0 to 14 instead of a scale from 10 to the 0 to 10 to the negative 10th. And so that is the pH scale. And that's where it comes from, is taking the negative log of the hydronium ion concentration. It ranges from 0 to 14. Again, these would just be the exponents. This would be 1 times 10 to the 0. H plus concentration, and this would be 1 times 10 to the negative 14th H plus concentration. And so again, just much easier to talk about 0 to 14, all the numbers are positive instead of these negative exponents. And so, probably beating the dead horse, but 7's neutral. That is when the H plus and the OH minus concentration are both 1 times 10 to the negative 7th. If we increase the concentration, what happens is the pH gets lower, and you can see some interesting pH values there. So a pH below 7 we refer to as acidic, a pH above 7 we refer to as basic. And over here you can see other things that are acidic and basic. We'll be dealing with biological situations. So throughout your body, you've actually got different pHs. So in your stomach, it's very acidic. In your spinal fluid, it's actually somewhat basic. And if you go in, let's say your significant other is pregnant and you think their water has broken, one of the tests that they can do is they test the pH of the vaginal fluid. And if the pH tends to be in the acidic range, then that is an indication that the membranes are still intact. This isn't a perfect test, but it's an easy test. Sometimes pregnant women just have leaky bladders with the baby dancing on the bladder. So sometimes you're not sure if that water is coming from the bladder or from a ruptured membrane. And so actually urine, you can see actually it actually varies quite a bit, but tends to be a little bit more acidic. So if it's urine, it'll tend to show up as acidic. If it's a ruptured membrane, amniotic fluid tends to be basic. So you run this test, turns out to be blue, you're going to be having a baby. If it turns out to be red, false alarm. For our body, if we deviate from a very narrow range of about 7.4 pH, you can get into alkalosis, which means that your blood is going basic, and that eventually leads to death. If you go lower, you lead to acidosis, and eventually that leads to death. So if you're in my organic chemistry class, one of the things that I always wonder about is this desire to have an alkaline diet to decrease your blood's pH, increase your blood's pH, decrease the amount of acid in your blood. And to me, that surely will cure all your diseases because it leads to death. That is one sure way to cure every disease is death. Now, if we take the Ka equation and the pKa, and your book does a derivation of it, you can actually end up with what is referred to as the Henderson-Hasselbalch equation. And this is very important because it relates pH and pKa, as well as the concentration of the conjugate base and the conjugate acid right here. Now, if these are equal, let's just say this is 1 times 10 to the negative, 7th, and this is 1 times 10 to the negative 7th. Well, this term right here, 1 times 10 to the negative 7th divided by 1 times 10 to the negative 7th equals 1. If you take the log of 1, that actually equals 0. And you get a very interesting result when the conjugate base equals that of the acid. And that result is that the pH equals the pKa. So pKa is a rank of the acidity, and pH is a measure of the acidity. And so this Henderson-Hasselbalch ranks this measure of acidity with this rank of acidity. And I'll explain that kind of right here. So when we titrate an acid, imagine it's down here. So we've got an acid, acetic acid, and we dissolved it in water. And then what we're going to do is just start adding base. And as we start to add base in there, we actually get this HA plus OH minus reaction. And that starts to deprotonate the base and give us the conjugate, deprotonate the acid and give us the conjugate base plus water. Well, let's just say that I had 1 mole of my acid in there, and I start to add in base. Well, as I start to add in base, you'd expect the pH to go up because I'm starting to add a basic compound. But notice the pH doesn't just skyrocket. It doesn't just go all the way up to 14. Well, why isn't it going all the way up to 14? Well, it's reacting with the acid. So as I'm adding the base in there, I'm using up the base in a chemical reaction. And so the base actually changes, the pH changes very slowly because you're using up the base. Now, if I get to this point where I've added half of the base, half an equivalent, so again, if I had 1 mole of my acid and I added half a mole of my base, I get to this equivalent point. And what that means is half of my base has been deprotonated. Well, if we look at that, I've got equal amounts of conjugate base and equal amounts of acid. Well, what happens if I put that back into my Henderson-Hasselbalch equation? So I've got equal amounts of my conjugate base, equal amounts of my acid. That turns into 1. The log of 1 is 0. And so my pH equals my pKa. So this is how we can actually figure out what I said is the pK is a measure of its acidity. Or actually, what did I say? Anyway, is a rank. pKa is a rank of its acidity, and pH is a measure of how acidic something is. So if you notice, if I want to figure out the ranking of this acid right there, what I do is I add half an equivalent of the base, and then I measure the pH. And that pH right there will actually equal the pKa. And that pKa is a physical property, and it tells us how acidic something is. The pH can vary. In fact, you can see here as I add more and more base, the pH will continue to go up until there's no more acid to deprotonate. And then as I keep adding base, that pH will just skyrocket because every time I add a base, it just goes into changing the pH. Every time I add the base here, it's actually going into a reaction. And it's reacting and reacting and reacting until I no longer have an acid to react with, and then all of a sudden the pH is just going to go up because I'm just adding more OH minus. So we can measure this property of how acidic something is by adding essentially half an equivalent of the base and figuring out what the pH is. So Henderson-Hasselbalch is a very important equation. Now, sometimes we get polyprotic acids, and will be very important for amino acids when we get to that section. And so sometimes you have multiple acidic portions. And this works, this titration to figure out the pKa actually works. So what we do is we start at the most acidic spot. So everything that can be protonated is protonated. Our amines are protonated and our carboxylic acids are protonated. And then I start to add the base. And again, when I get to half an equivalent of the base, half of the most acidic proton is going to be deprotonated. And the most acidic proton is the carboxylic acid. That's why they call them acids. They're the most acidic. And so you'll notice at this point right here, where we have equal amounts of the protonated form and the deprotonated form, we get kind of a little inflection point in our titration curve. And if we measure that pH, that tells us the pKa there. So the pKa of that carboxylic acid is 2.34. Now, as I add more and more base, I start running out of protons to deprotonate off of my carboxylic acid. And eventually I get to a point where I have completely deprotonated my carboxylic acid. And I end up with a species that is what we refer to as isoelectronic. It actually has equal amounts of positive and negative charge. So overall it has a negative charge. It's a Zwitter ion. And that's its isoelectric point. Now as I add more and more base, notice how the pH just skyrockets here. Because every time I add an OH minus, it simply goes into increasing the pH. But then all of a sudden, I get into a concentration where it is strong enough to deprotonate the amine, which is less acidic. So I get enough OH minus in there that I can now start to deprotonate this amine. And again, when I add just enough, again, it's going to be 1.5 equivalents, 1 equivalent to completely deprotonate that, and then half equivalent to deprotonate half of my amines. I get this inflection point, and that's going to be the second pKa. And then as I go and add more and more, then again, the pH is going to skyrocket again. Okay, so those titrations are very important because that's how we can actually figure out the pKa's, which we put in table forms and use to look at how acidic something is. We determine that pKa's by measuring the pH through these titration curves. And we see some interesting things. So with different types of acids, what we get is kind of this linear portion where the pH doesn't change much. So look at this green band right here. The pH isn't changing much. I'm adding lots of base down here, but the pH is only varying, from, at most 2 pH units. And so if we could actually pick this spot right here in the middle, I'm going to ask you a question. If I add acid, what's going to happen to this reaction if I have equal amounts of this acid and this conjugate base here? I'm going to add some acid here. Well, if I add acid, what happens is it's going to protonate my conjugate base, and I'm actually going to start moving in this direction here. Okay, I'm going to shift the equilibrium to the acid side. But notice my pH doesn't change much. It changes, a small amount, but gosh, look what happens over here when I add a bit of acid. I add a drop and boom, all of a sudden I'm down at pH of 1. Here, I add a bunch of acid, in fact, 1/10 of an equivalent, and the pH only drops, a little bit of a unit, half a unit. So these are what we refer to as buffers. These resist change. So a buffer is a weak acid and its conjugate base. And what's cool about them is if you pick the right pKa there, they resist change, because if I add base, I'm going to start going over here and start pulling off some H's, and you notice the pH doesn't increase much. If I add acid, I'm going to start going this way, and again, the pH doesn't change much. If all I did was add acid into a solution, all of a sudden, you know, let's say I had a pH of 7 and I added some acid. It depends on how much you add, but just a few drops, all of a sudden you can find yourself down at a pH of 3 just by a few drops of acid. And that would be bad for our biological system because we realize that for us, we want our reactions to occur in a very narrow pH range. So our blood is buffered. In fact, our body's buffered everywhere. And so what we do is we pick buffers that actually prevent dramatic pH changes. And so you can see here's 3 different acid-base combinations that resist pH changes. These amines resist pH changes at just above 9, this around 7, just below 7, and this around 5. So the question is, would this one down here, would this be a very good buffer if I wanted to keep my solution at a pH of 7? And the answer would be absolutely not, because if I was at a pH of 7, you can see that most of your green example here is deprotonated. If I want to keep a pH of 7, what I do is I want to pick a buffer that has a pKa close to the pH that I want to operate at. If I want my solution to be a pH of 9, I would choose this. If I wanted my solution to be a pH of 7, I would choose this as a buffer. If I wanted my solution to be a pH of 5, I would choose this as a buffer. If this green one down here, if I was trying to make a solution of pH 7, that has no buffering capacity. If I added base, the pH would just skyrocket. If I added acid, you can see if I added just a little bit of acid, the pH would drop dramatically. So buffers only work around their pKa. So here is a triprotic acid. So this actually can buffer at 3 different pHs. Okay, I'm dragging on here. So here is a list of a bunch of different acids. And so you can see their pKs. And so some of them have multiple pKs, like oxalic acid has a pKa here, and then it has a pKa there. So I'm going to pick a pK or pH that I want to buffer at, and you pick the best buffer. So let's say I want to buffer at 7.47. What would be a good buffer for 7.47? Well, the best buffer would be what we refer to as HEPEs here, because that has a pKa that matches right with 7.47. Now, MOPS wouldn't be too bad. It's close to 7.47. Tris wouldn't be so bad. You know, it's got less buffering capacity. And so kind of the general rule is what you do is you pick a buffer that's plus or minus 1, well, actually not even 1 pK, so kind of plus or minus 0.5 pK units from the pH that you want. So again, let me just do that one more time. Let me just randomly, so someone send me a number. The person that said 8.5, okay, I got it. So 8.5, I look and I say, okay, well, I don't have a perfect buffer, but I'm going to choose either, I'm going to choose Tris. If I chose boric acid, that's going to be 0.74 units away from my pKa. So that's not going to be as good of a buffer there. So Tris would actually be a better buffer. So this is by far not an exhaustive list of all the compounds that can actually act as buffers. There's a tremendous amount out there that would probably match your desired buffering capacity. So here's just an example here. If I had 1 liter of water that was pure and I just added 0.01 moles of a strong base, very, very small amount of a strong base, the pH shoots up to 2. If I added 0.01 moles of a strong acid, ooh, there's a mistake, HCl, then the pH goes down to 2. Now we buffer it. We're going to buffer it with this phosphate buffer here. We can actually figure out when that pKa is. So if you look at that, that's HPO4, H2PO4. So what we're going to do is go look for that. I think it's on here. Yeah, right there. So that's got a pH or pKa of 6.82. So yeah, if we want to buffer around 7.2, that would be a decent buffer. So within 0.5 units. And you can see that if you add a base, the pH only goes up just a little. And if you add the same amount of the acid, the pH just goes down a little. So dramatic, you know, I buffered it, I prevented it. In the unbuffered solution, it drops to 2. Here it drops by 0.1 units. So buffers are very important. In our body, we use a bicarbonate buffer. It involves the lungs and exchange of CO2. And our kidneys are actually involved in that buffering. Again, we'll talk about this later. And essentially, this allows us to control the pH of our blood, which is very important for control of reactions. And so here you can actually see the pKa's of the different components of the bicarbonate system. And so here is the pH that we operate at. And so we actually do get some buffering from the CO2-ish, well, sorry, the carbonic acid, sorry, the bicarbonate, which is the blue line, and then the carbonate anion. So we actually get some buffering there. Oh, actually, sorry, we don't get it from the carbonate ion. Oh, it must be time to end this. Anyway, we actually get mainly buffering from the bicarbonate here. So if we add a base, what would happen is we would deprotonate this and make carbonate. If we added an acid, we would protonate it and make carbonic acid. So, and that's what allows us to maintain our body, or at least our blood, at a pH of 7.4. Okay, that was a long one. So those are the checkpoints. Oh, and I'm losing my exponents. So I'll fix those. And I'll post this. And hopefully someone will come in and ask me questions in office hours tomorrow.